Hello, everyone. Welcome to the fifth and unfortunately the last day of Understanding Deep Learning. Um, this this event is organized by Data, Student Data Science and Machine Learning Group at the University of São Paulo. My name is Tel, and I would like to thank the USP, the University of São Paulo, and the ECMC, the Institute of Mathematical and Computer Science, for the support in promoting this event. Thank you, Luis, for accepting our invitation. We're very happy to have you here today. Luis Serrano is the author of Grokking Machine Learning and the creator of the popular educational YouTube channel Serrano.Academy. He has worked in large language models at Cohere, in artificial intelligence at Google and Apple, and has a quantum AI research scientist at Zapata Computing. He has popular machine learning courses on platforms such as Udacity and Coursera, and has a PhD in mathematics from the University of Michigan and a master's in bachelors from the University of Waterloo. I strongly suggest you to watch and to search for his YouTube channel. I will put the link soon here in the chat. And he has also a blog, a very interesting blog that I will post here in the chat soon as well. Feel free to ask questions during the talk. Serrano will be looking for the questions, but nevertheless, at the end we will have like a question and answer section. Okay. Before we begin, a quick disclaimer for the Portuguese-speaking audience. Oi, gente, essa palestra vai ser totalmente em português, desculpa, em inglês. Então, se você tem dificuldade em acompanhar a palestra, ao final, quando acabar, daqui a algumas horas, vai ficar disponível a tradução automática, que está muito boa. Acho que vocês vão conseguir olhar por lá depois. Certinho? Okay, Serrano, we are ready to go. Good presentation.
Obrigado, Theo. Thank you. Boa tarde a todos. Like Theo said, I don't speak Portuguese. I'm Colombian, so I speak Spanish. So we could have a conversation, me speaking Spanish and you speaking Portuguese, and it would work out. But I'll speak in English. And thank you for the invitation to you and the University of Sao Paulo and the Data Science Group. It's a pleasure to be here, and it's nice to follow my friend Joao. So I really enjoyed his talk. I've had a lot of great long machine learning conversations with him. Actually, he has some input in the stuff here. My talk will probably be the most basic one. I know this is a very educated crowd. I will talk about basically transformers, how they work, how I see them. Nothing new, but I do see them in a particular way. I like to see machine learning in a very geometric way, in a very pictorial way. So yeah, and I have the chat right here. So I do see it. Feel free to ask me any questions, and I will try to answer them in real time, or make breaks or answer them at the end. But just throw any question or any comment, and if we go in a tangent and end up talking about something different, well, that's even better. And sometimes I will have questions for you, so I will make some sort of easy quizzes of easy quiz questions for us to interact. And thank you. I see that the channel has been shared in the link. So yeah, definitely take a look at it for a lot of educational material on machine learning, LLMs, etc., etc. Anyway, so today I will tell you about transformers. So transformers, something really important was introduced in this paper called Attention is All You Need by several authors. And this is the architecture they had there. But I like to see them in a much more simpler way. So I like to see them as transformers like this. And something that really blew my mind when I first heard how transformers and ChatGPT and all this works. I knew they generated text. What surprised me was that they generate text one word at a time. I really thought it through. I thought it would just kind of figure out something to say and then refine it the way it does for images, right? Like an image, it just makes something rough and then it refines it and refines it and refines it. It doesn't do it pixel by pixel. But when I heard that it generates words one word at a time, like it's pretty much like you say, hello, how are you? And it just comes up with the next word, doing. And if you want to create a story, let's go you say write a story, and then it really only comes up with the next word, which is once. That's it. And then if you want more words, you just have to put more words in the input, right? Like you say, write a story once, and then it says upon, write a story once upon, and then it says and so on and so forth. And somehow it comes up with amazing stuff. That drove me crazy. But it does make sense in the fact that it's not so good at going forward, not so good at coming up with the next word, but really good at looking back. And one of the reasons it's really good at looking back, well, it's because we have more computers, more data, more processing power. But the other one is attention, because attention tells it where to look. So we'll see. We'll see about that today. But in particular, generating one word at a time is nothing new. It's really not even from generative machine learning. This is something that came from 10 years ago, discriminative machine learning. If you use, WhatsApp or any text messaging, this is nothing new. When you write something, it generates the next word because it suggests the next word in a sentence. So this is generating one word at a time is not a new concept at all. And it would just simply be a neural network, right? A neural network would say if you input a sentence, it suggests the next word. So it could be, this is a very oversimplified version of the neural network, but if you have all the words here on the left as input and all the words as output, the neural network would just sort of suggest, based on the words of the sentence, what comes next. Obviously, I said this is oversimplified, but you can have something recurrent, or you can have LSTMs, or something convolutional, just different architectures. But at the end of the day, this happened 10 years ago. I don't know if you've ever tried this. Don't try it with friends, because you'll start losing friends. If you continue pressing the middle word, the suggested word, you'll come up with some crazy things. I just started doing it. It says, hello, how are you feeling this week? All your kind wishes for a wonderful weekend with your kindness and happiness for your family, blah, blah, blah. Makes no sense. However, every few words make sense, right? Hello, how are you feeling? And happiness for your, because it has a small memory, right? It's an RNN, or a recurrent neural network with a not so large memory that can come up with little things, but it's not going to come up with a really long, the kind of answers you've seen on that transformers provide. So we basically need something more advanced, and that's why the transformer architecture comes in. This part here is the neural network. A feed forward is just the plain vanilla or advanced RNN or something neural network. And what really does the magic is attention. Really, the attention is what pushed the transformers through one level to really be able to start talking. So I don't like to see the architecture like this. I like to simplify it in my own way. So we have an input and we have an output. And let's say the input is write a story. And first, that goes through a process of tokenization. I'll tell you what all these things are. Maybe you know them, but I'll tell you in my way. First, it goes through a process of tokenization. Then that goes into something called an embedding. Then it goes into something called positional encoding. And then the meat of the transformer happens, which is you have a series of transformer blocks. Each one of them, before we had a neural network with a bunch of layers. Now we have, each one has an attention layer attached to it. Okay. I put 3, but you could have tens or more. Like you can have many layers, hundreds of layers of this. But think of it, if you know neural networks with a bunch of layers, now you have a bunch of layers, each one with an attention attached to it. This is the meat of the transformer, and then you go to a last step called the softmax, and then boom, the word once appear after all this stuff. So as I said, this part is the neural network, this part is the attention, and we'll go over every single part of these ones today. Oh, sorry, I have this twice. But first, let me start with one that's not feed forward or attention. Let me start with embeddings. So embeddings are over here, and they're over here in the big architecture. And to me, embeddings are the most important thing or one of the most important things in machine learning, even though I've been selling attention here as the important thing. Embeddings are crucial for us to do anything with images or anything with text or anything with audio or video, because they're the translation between humans and computer, right? Like we have, when we talk in words. A computer talks in numbers. So we need a good bridge that would connect them, the two. And if embeddings get better, language models get better immediately, because they are where the translation happens. So I'm going to start with a very easy quiz. And the quiz is the following, and it's also a test of how much lag do we have in the video, because I want to ask you something. So I have an embedding here, and I have a bunch of words in the plane, and their coordinates are here. Of course, the first coordinate is the horizontal coordinate. The second one is the vertical coordinate. So for example, banana is 6 and 5. So I see already there are answers. Where would you put the word apple? So I'm going to give you 3 options to make this easier. Bruno already gave a really good answer. A, B, or C. So I want to hear where you would put the word apple here in one of those. Which one of those 3? And I'm also checking the lag here. Right? So Bruno says 5, Joao says C, Wilbur says C. Very good. I would put it in C as well. And the reason I would put it in C, obviously, is because fruits should stick together. It's not going to go in sports, it's not going to go in houses, and it's not going to go in vehicles. So we put it in C. Simple, right? That's an embedding. Now, this embedding has 2 coordinates per word, and an embedding would have lots and lots and lots. I've seen them up to 4,096, but let's think of 500 or 1,000 numbers per word. And I like to think of this as describing it, right? Like they're describing the word in some way. This is some property of the word. This is some other property. Some of them we may know, maybe size, maybe flavor, maybe color. Some of them the computer knows. And we just, it just happens to have associated certain things. Okay, now let's do another quiz. So you help me out. You're going to tell me if top right or bottom left. And here we have a strawberry and an orange. And here we have a phone and the logo of Microsoft. Okay, so you say top right or bottom left. Where would a cherry go? Top right or bottom left? Let's give it some time for the lag. So Bruno says top right. Very good. A cherry goes top right. Where would good job, everybody. Look at you all. Where would an Android go? Yep, I see some bottom lefts. Very good job. Because the Android would go on bottom left. Now let's go. I'm going to go a little faster. Where would a laptop go? Yep, laptop is bottom left. Where would a banana go? Banana is top right. And now where would an apple go? That's the question. Ha! Luca just guessed it a little bit before that apple's going to be the catch. Good job, good job. So where would the word apple go in this embedding? That's difficult, right? Like we don't really know where apple would go, because it's kind of, I don't know, let me just, if it's a fruit, it should go on the top, right? But if it's the logo, the company, then it should go on bottom left. So the question is, where would you put apple in this embedding? And the answer is, we don't know. No matter how good an embedding is, I could create the best embedding in the planet using all the computing power and all the data in the world. It still wouldn't know where to put apple, because a human wouldn't know where to put apple, right? Like if I stand in front of you and I say apple, you don't know what I'm talking about, right? So embeddings don't, no matter how good an embedding is, it's not going to get there. It's not going to do the entire job because we have this problem. So we have the problem of words meaning 2 or more things. So how do we solve this? We solve this with attention. So attention is what gives it context. Because if I stand in front of you and I say apple and you don't know what I'm talking about, the first thing you would ask me is for some context, right? You would wait until I say more words, because the other words around what I say are going to give it away what I'm saying. So the computer needs to do this. There's no choice. There's no embedding. That's good enough. So attention happens here. There's a scale dot product attention, and there is a multi-head attention. And we'll talk about both. But basically, the multi-head attention is a bunch of scaled dot product attentions working together like a team. So these are the formulas, blah, blah, blah. We'll get there. But basically, the idea is to use context. So help me out with this question. I have the sentence, please buy an apple and an orange, and Apple unveiled the new phone. And obviously now you know that in the left, I'm talking about a fruit, and in the right, I'm talking about the phone, about the company. But what word gives it away? Like, which is the word in the left and which is the word in the right that made you think, right? It's not the word and, it's not the word please. Which is the word in each one that said, you know what, I think I know now what you're talking about. So help me out here, and I'll pause a little for the lag. What are the words that did it, right? Ricardo's correct, says orange and phone, right? Because when I said please buy an apple and an orange, you figure out I'm talking about an apple. When I say Apple unveiled a new phone, I'm talking about an apple. Somebody once pointed out to me that, yeah, of course, Orange is a phone company in Europe as well. So this can always, all my examples, no matter what example I come up, there's always some ambiguity. So just bear with me. But that's the idea, right? And so what's going to happen is I like to see attention like gravity, like words pulling words, because the word orange is going to pull the word apple, and the word phone is going to pull the word apple in another direction. And so basically we have, let's say, this embedding. Imaginary embeddings are, of course, 1,000 vectors of length, 1,000, but I'm going to think of them as vectors of length 2 to go graphically. But if you just picture things happening in 1,000-dimensional world, is the exact same phenomenon. We have an orange here, we have a phone here, and here we have some ambiguous apple that we have no clue what's I see Fernando just said phone is a delightful fruit somewhere in this universe. Yeah, that sentence will completely throw this model away. And we can always do that, right? Like we can always come up, there's always a sentence that confuses it, but the idea is to, like in the same way that we can confuse ChatGPT with some ambiguous input. But yeah, let's do it for this simple one. The word orange pulls the word apple towards it, right? So let's do that. The word orange pulls the word apple towards it, kind of like gravity, right? Or like a magnet. And then the word phone pulls the word apple towards it. Okay, so attention works that way. First, I'm working with the coordinates of apple. The coordinates of apple are here, like maybe 6, 6 or something, right? But if I talk about an orange, then the orange pulls it, and my new coordinates of apple are here. So now the transformer is working with these coordinates. And here, when I'm talking about the phone, the transformer is now working with these coordinates on the bottom. That's the idea, right? Now, as humans, we knew that the word orange pulls the word apple, but a computer doesn't know. A computer won't know, oh yeah, it's orange, the important word. For a computer, the word and is just as important. So it's not going to be able to discriminate just yet which word influences Apple more. So it kind of has to pretend that every word influences the word apple. We have to pretend that, but that's no problem, because then we look at it like gravity, right? Imagine this. You can think of them as magnets that are far away or close by, or also like planets that are far away and close by. And planets that are close pull each other strongly. For example, apple and orange have a strong pull because they're close in the embedding. On the other hand, apple and all the other words, they're far away if we have a good embedding. And so their pull is pretty weak. And so apple and orange pull each other strongly. Notice that they both pull each other, not just apple, everything pulled each other. In the same way that, the moon and the earth, imagining that everything has the same mass, imagine that all the planets have the same mass, the earth and the moon pull each other much more strongly than the earth and Jupiter, right? Because they're very far away. So in this way, every word pulls every word, just so little when they're far away that is pretty much negligible, and only the similar words pull you. right? So that's pretty much the idea. And context pulls, right? Because if I've been talking about fruits for an hour and then I say apple, then you're pretty sure that I meant the fruit, because I have a galaxy here of fruits that I've been talking for a long time. My context in high dimensional space, my context has a big galaxy here of fruit related things. And so everything I talk kind of goes there, gets pulled in this sort of big galaxy through gravity. And so the word gets pulled there, and then the context, and then the transformer knows that I'm talking about a fruit. If I've been talking about computers for a long time, there'd be a big galaxy here, and it would get pulled. So that's the idea. Any questions? I'm looking at the chat, and it seems like if you have any questions, feel free to put them in the chat, and I will continue. But first of all, a small lie. I've been telling you distance a lot. I've been saying the distance between two words, the distance, pull, not distance. It's similarity, but it's very similar. Basically, similarity would be opposite of distance, right? If I have words like cherry and orange, they're very close. They're very similar. So distance is low, similarity is high. And if I have phone is far away. So high similarity, low similarity. So low distance, high similarity, high distance, low similarity. And there's 3 measures of similarity. Again, this is a knowledgeable crowd. Maybe you saw them, just bear with me. The first one is dot product, which I like to see it as a way to sort of combine similar properties. So I'm going to be very optimistic here. I'm going to assume that I have an embedding with 2 dimensions, and one of them is how techy the word is, and the other one mentions how fruity the word is. And I have my words here somehow ended up there. Obviously, the fruits have high fruitness and low tech, and the phone has high tech and low fruitness. And they are, the phone and the cherry and the orange are very close by, whereas which have high similarity. And so let's calculate their similarity. So I'm just going to put their coordinates together, and the first one is tech and the other one is fruitness, and then I'm going to multiply the tech and multiply the fruitness and add them together, and that's a high number because the fruitness was high for both, right? Now, if I do cherry and phone, then it's not the same, right? Because I have here, this one has low value for tech and high for fruitness. This one has high for tech and low for fruitness. So we're not going to end up with a very high number. 1 times 3 plus 4 times 0 equals 3. And then the other example, even worse, orange and phone, I have 0, 3, and 3, 0. The dot product of those is 0 because when I have tech, I have no fruitness, and when I have fruitness, I have no tech. So I get 0. So they're orthogonal. I could even go as far as minus and negative numbers if you are diametrically opposite. But basically, this dot product, imagine it doing for 1,000 vectors of length 1,000, is just the product of the first coordinates plus the product of the second coordinates, etc., etc., etc. It's high when you have 2 similar vectors. It's low when you have 2 different vectors. Another one is cosine similarity. So cosine similarity is just the angle between them and the origin. So these 2 have a really small angle, 14. I'm going to take the cosine of 14. That's a very large number, very close to 1. And if I have these ones, their angle is 76, which is a small number, so 0.24. And for these that are perpendicular, their angle is 90. And so I have cosine of 90. So cosine similarity is better for text than distance, because some vectors could be long and some vectors could be short, but if they're pointing in the same direction, they have similar meanings. So yeah, so that's the idea. And why did I mention 2 of them? Because they're actually almost the same thing. Dot product and cosine similarity are very similar. If I scale my my vectors to length 1, so if I take every vector and make it become length 1, then dot product and cosine similarity give me the exact same thing. So if I bring everything to the sphere, the circle of radius 1, then I get, if I calculate the cosine similarity and if I calculate the product, I get the exact same number. Now the question is, and here in the architecture, there's a math mole. Now the question is, which one do you use for the transformers, dot product or cosine similarity? And the answer is neither one. It's some other one that is still similar, because dot product and cosine similarity are scaled one from the other one. This is also a scaling, it's just a different scaling. So if I were to do the dot product between 1, 4 and 0, 3, I get 12. But instead, I'm going to divide it by the square root of 2. And the same thing for this one. So I get 3 divided by square root of 2. And the 0, I also divided by square root of 2. Why square root of 2? Because it's the length of it's the number of entries in the vector. So if my embedding has 1,000 entries, I just take the dot product and divide it by the square root of 1,000. That's what they did. That's the scale dot product. And my guess is that it worked because it doesn't become too big. And the square root there is to bring it down, so it's not, so you don't blow up if your embedding is really big. And my guess is that it kind of worked, and so we did that. Let me address some questions here. Fernando says sometimes 1 minus similarity gives an actual distance. Okay, that works. That may work for some metric spaces, depending on the similarity. Yes. And Eduardo says median Euclidean distance. Let me see. That may work, but the problem is that Euclidean distance blows up too much. And I kind of want, if two things are 10 kilometers away or 1,000 kilometers away, I want their similarity to be 0, right? And so the good thing of similarity is that like distance can go from 0 to very, 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 very large, whereas similarity can just say, you know what, things are far away, where you're pretty much 0, and if things are close, then it changes, and it's closer to 1 or something. So yeah, this is pretty much the calculation. Now let me get to what happens with this formula with similarity, right? So let's do I said gravity, right? I said these things were like gravity, and gravity kind of works like g times mass 1 mass 2 over r squared. That's not what the case is, but we have a similar formula, a formula that is not the one for gravity pull, but it uses similarity. And here's an example. I want to turn my apple. I have my apple vector, and I turn it into apple plus something orange, right? Apple plus a bit of orange. And as a matter of fact, I want percentages. But how much orange I want? Well, how similar are they? And the more similar they are, the more orange I put in apple. And if they're very different, I put nothing. And I want this to add to 1. So I want to turn my apple into a percentage of apple plus a percentage of orange. And the more similar they are, the more orange. So let me give you 2 small examples. Let's say if things are far away, then if it's apple and truck, then I want a much smaller proportion of truck added into apple. So let's do this. Let's say that my similarity between apple and orange is 0.7, which is high, thinking of cosine distance. And my similarity between apple and truck is minus -6, because they're so similar. They're so dissimilar, it's a negative similarity. Let's see what the gravity formula works for each one. So here I want to say that apple becomes apple plus 0.7 orange, because I want to add a lot of orange to it. I want the orange to pull it strongly. And here I want to say apple equals apple minus 0.6 truck, because I don't want so much. However, I want this to be positive. You may have seen this in machine learning a lot. You want things to be positive. I don't want to be adding negative stuff. So what do you do when something you want it to be positive? You just take e to the that, right? So let's, instead of 0.7 and 1, say e to the 1 and e to the 0.7, and then here say e to the 1 and e to the negative 0.6. This number is really small, so there you can see that I'm adding very little truck to apple, whereas this number is bigger, so I'm adding a lot of orange to apple. But then I want to normalize, because I want these to add to 1, because I want a percentage, right? So I divide by their sum, right? I divide by e to the 1 plus e to the 0.7, and I get this much. I get apple now becomes 57% apple plus 43% orange. And here I get that apple it becomes 83% Apple plus 17% truck, which is much smaller. I really would want 0.0001 truck, but this is just a playful example, right? And why do I want this to add to 1? Because of linearity, right? So this is my formula. And the reason I want these numbers to add to 1, this 0.83, 0.17, and this 0.57, 0.43, is because I want to move in a line, right? Like if I have my coordinates here for Apple, and now I think of 0.57 Apple plus 0.43 orange, the fact that these two add to 1 means I'm moving along this line 43% along the way towards Apple, towards orange, right? And if I were to have that for phone is Apple times 0.64 plus phone times 0.36, then I'm moving on the line towards phone 36% along the way. All right. And now, so that's that's the analog of the gravity formula. It's a softmax of a similarity addition. If you ever see it, like if you see it on the paper, it says softmax of the dot product of the matrices, and so that's what it is. So now let me give you a small example that always happens with attention. It requires a little bit of faith because it's a small example with some words, but attention always shows this example. The bear ate the honey because it was, and then you don't know what the next word is, right? But the idea is, or if you've seen this, or with different analogs, right? The chicken crossed the road because it was, or something like that. So the bear ate the honey because it was. The question that I have is, what does the word it refer to here? Does it refer to bear, or does it refer to honey? Well, it could be either way, right? Like even the biggest model with all the data and all the computing power will not know what it's talking about because we need a next word. If the next word is, for example, hungry, then I'm talking about a bear. The bear ate the honey because it was hungry. If the next word is delicious, then the bear ate the honey because it was delicious. Then now I'm talking about the honey. So what does this mean in terms of attention? So let's look at the attention as gravity. Okay. Uh, Again, this requires a bit of faith. It's a very toy example, but let's imagine that the connections with it and honey and bear are strong, and the other words are negligible because they're always there, and also because, let's just say, they're far away. So let's forget about them. Let's think of honey, it, and bear. And it has no idea if it should go to honey or it should go to bear. It is confused, and it's right in the middle, let's say. So now if I were to throw in an extra word, the next word is going to help, because if the next word is hungry, well, in an embedding, hungry is similar to bear, let's say, because bears are hungry. I could change the words. They describe each other more often. Let's say that hungry and honey, let's say. And so now I have two pulls to the right and one pull to the left. So now it just goes, kind of walks towards bear, and now I know that it describes bear. On the other hand, if I had the word delicious, well, honey and delicious appear more in sentences. Honey and delicious are very more similar, so we can imagine that they are more closer in the embedding. So now I have more pull towards honey than towards bear. And so I get closer, and then it is less confused. Now it knows it's talking about honey. As I said, this is a little faith here, but you can see how the idea of like context pulling you in a huge high dimensional space helps you understand what you're talking about, right? Now, any questions so far? This is pretty much the one attention, and now I'm gonna get to more to multi-head attention. Feel free to throw them in the chat. And I will stop. We have a problem because sometimes the embedding is not that great. So we're gonna have to improve the embedding. So I have a question for you. Do you think one embedding is good enough? It's a very loaded question. I always ask it in the way of saying no. One embedding is not good enough. Some embeddings are strong for some things, and they're weak for other things, and we're gonna have to live with that. Okay, so ideally we would like to have a lot of embeddings. Now, it's hard to get embeddings, but before we get there, I'm going to ask you a small quiz. The quiz is I have 3 embeddings, and you can help me. Tell me which one of the 3 is the best one and which one of the 3 is the worst one. And by that, I mean, try to interpret it in your own way to see what would be the case. But here I have in each one of them, I have the phone, the orange, and the ambiguous apple. So in order to play our game with gravity, which one of these 3, A, B, or C, or 1, 2, 3, is the best one, and which one is the worst one? And then Bruno says, yeah, it depends on the application, absolutely. But this one is a small example. Imagine for only this case. And Eduardo says, yeah, we have more dimensions combined. We will combine dimensions. So it's Hickson. I'm sorry if I'm not pronouncing it well, but it's Hickson says the first one. Yes, you are correct. The first one is the best one, right? And which one is the worst one? So the first one is the best one because it really separates apple and apple, right? Like it's really good at that. On the other hand, the worst one for me is the second one. The second one is not so good because when you play this game, it doesn't really separate the apple and the apple. So this one's bad. And then the third one is kind of so-so, right? So yeah, good job, everybody. So the first one is the best one, the second one is the worst one, and the third one is kind of so-so. But this may happen for some things. An embedding may be really good for fruits and bad for vehicles, and the other one be, we kind of want to combine embeddings. I would do is maybe go to different research groups and go to different places and try to find these different embeddings. But that's hard. I see that some more answers are appearing, and yes, Carlos is correct. People are correct that the first one is the best one and the second one is the worst one. So I could just go to a bunch of places and get different embeddings, right? I could go to one research group, go to University of Sao Paulo, they have a good embedding. Go to Google, they have another good embedding. And then combine them, make them vote or something. But that's hard because first of all, I can't go around the world asking for embeddings. They're hard to build. And also because if one has different dimensions than another one, I don't know how to combine them. So I kind of have to live with one. Let's live with one embedding, and let's try to modify it and see if we can get more embeddings for free. Okay? So let's do that. And how do we modify embeddings? With one of my favorite things in the world, linear transformations. Okay? How do linear transformations are matrices, basically. But I don't like to see matrices as matrices. I like to see them as drawings. So let's say we have a dog, okay? An image of a dog. I could do several things with this image. I could rotate it any number of angles. I could stretch it horizontally. I could stretch it vertically. I could stretch it in any direction. And I could also do a shear. So what a shear does is like pretend you have a book, the cover of a book, you put it towards the table and then push the top. Okay, so a shear. It's not a rotation, it's not a stretching, it's a shear. And a linear transformation is any combination of those. I can rotate, stretch, rotate again, shear, then rotate, then shear, shear, then stretch, and I get something like that. A good way to look at it is take the 2 fundamental vectors. In this case, it's 2, but if you have 10 dimensions, it's 10, and send them to anywhere. So send this blue vector anywhere, send this yellow vector anywhere, and then the plane follows, right? Because the plane is made of these little squares. Well, now it's made of these little parallelograms. That's an embedding, okay? So a 10 by 10 matrix is some linear transformation in 10 by 10 space that does it, linearly, stretching, shearing, rotating, etc. And that's what we're going to do to create new embeddings. So now I'm going to ask you the same quiz as before. I have an embedding. I have one transformation of this embedding and another transformation of this embedding. Now tell me which one is the best one and which one is the worst one. So notice that I transform it, right? Because I turn this into this parallelogram and then into this other parallelogram. I don't know what the matrix is, but which one do you like the most? Like which one of these 3 would be the best one? So Bruno got it correct. Yes. And Letty, the best one is on the right. And it seems like the worst one is that second one, as Alexander says, right? 2 best and sorry, the second one is the worst one, and the third one is the best one. Check it out. Why is, so let's do the gravity game on the three of them, right? So this one is okay because it kind of separates apple and apple. This one is bad because it didn't separate apple and apple. And this one is fantastic because look what it did. So the same embedding, notice the same embedding, which is embedding 1, that's the one we have originally, that's the one we built and we're working with. One transformation made it awful, another transformation made it awesome. And so the idea is to apply a bunch of transformations, and some of them may work, some of them may not, and we train those transformations like a neural network, okay? And so the neural network starts learning when a transformation is good and when is it bad and for what things. That's multi-head attention, okay? So the idea is to get new embeddings from existing ones. Oh, sorry, I think I have a lot of repeated stuff. Apologies for that. And the idea is to score them. So imagine a neural network. We'll get to this more in detail, but imagine a neural network being able to score an embedding. So for example, the okay one gets a score of 1. The bad one, let's say, gets a score of 0.1. And the good one, let's say, gets a score of 4. And my big embedding is going to be a combination of, the last one gets 4 votes. The first one gets 1 vote. And the second was 0.01 vote because 0.1 vote because it's the bad one. That's multi-head attention. Okay. So in multi-head attention, we have, let's say we have our embedding here, our original embedding. This is our plain vanilla embedding that has the apple, the phone, and the orange. And then there's something called the K and Q. I haven't told you what they are, but the K and Q, key and query matrices, are the ones that build a bunch of embeddings. So you build a bunch of, you find a bunch of random transformations and you apply them. And then this part over here, the scale.product attention, is able to score them. So it basically, this one makes it really tiny, this one makes it really big, and this one keeps it, depending on how well they do. And then concatenation puts them together. So you put them together into a bigger embedding. I'll tell you a bit more about how it gets put together in a little bit. That's the linear step. Okay, so this is pretty much what's happening here. This is an embedding that has context. If you have any questions, feel free to throw them there. I haven't told you the whole story because I haven't told you about the values matrix. So this is the key matrix, the queries matrix, and the value matrix. I haven't told you what the value matrix does. But before I get there, let's do a small recap, right? So this is scale.product attention, and this is multi-head attention. All of them have the KQV, but notice one thing. Do you remember that we did the dot product? The dot product is this KQ transpose here. That's the dot product. And this square root of dk is when we divide it by the square root of the number of entries in the vector. Remember, if it was 1,000 entries, we divided by 1,000 square. This is the scaling. Then we did the softmax. Remember, we did the softmax to do the gravity calculation. So there's the softmax, and then this v is coming up. But that's the idea. So I'm going to tell you about the key, the query, and the value matrices. And as I said, I'm gonna leave the values for the end, and I'm gonna tell you about key and query matrices now. And basically what happens here is just linear algebra. So if you love linear algebra, go for it. If you don't like it, then just zone out for the next minute and a half. But basically the idea is that I want to get these three embeddings using the key and the query matrices, the okay one, the bad one, and the good one. And it all happens with similarity. So remember, we did similarity with dot product, right? So similarity, let's say I have a vector for the orange, let's say of length 3 for fun, and a vector for the phone, let's say of length 3. And when we calculate the similarity, we did the dot product, right? Dot product, I can put it like a matrix multiplication, which if you scale it, it is the cosine distance. So I'm gonna pretend they're the same thing in a scaled world. It measures the angle, the cosine, and it also measures the dot product. Now, if I have a key and query matrix, I'm multiplying each vector on one side by the keys matrix and each vector on the other side by the queries matrix. So now I'm modifying all my vectors in my embedding either by the keys or by the query, depending on if you're the first or the second one that I'm taking the similarity. And what does this do? Well, my new similarity is the first one, which I won't forget that I'm multiplying by the key matrix, times the second one transposed, which is query matrix transposed times phone transposed. And then this part, I'm just going to take it as one thing. Key times query transposed, I'm going to take it as one thing. And that's a linear transformation. So that's the same as finding the angle, not in the original, but in the modified embedding. So I'm looking at angles in a modified embedding, okay? And so basically, the similarity here is this angle. But if I transform my embedding using the key and query matrices, I get a similarity in a different embedding. And this may just be a better one, okay? I'm going to stop to answer a question from Fernando, which says, what are the families of transformations that you allow? Anything linear. I guess I just answered it. But yeah, anything linear transformation, right? So anything that's a matrix, basically. Think of a matrix. If you multiply your vectors by that matrix, you get a linear transformation. Sometimes they are degenerate. Sometimes you can send it to something of smaller dimensions. Who cares? They never happen, probabilistically speaking. But yeah, that's the idea. And I'll get to your question, but yeah, question. So now we get to the values matrix. And to be honest with you, this one confused me a lot. And I did what I do when I'm confused. What I do when I'm confused is I ask Joao from the previous talk. I just asked Joao, and so one day we used to work together. I just asked him until I finally, got he has a very strong idea of how these things worked. So the idea of the values matrix is much, much more subtle than the key and query matrices. And so I want to tell you, it's a little more sort of, there's a bit more faith involved here. But imagine this. I have a really good embedding to calculate my similarities, right? Now, that may not be the best embedding for talking, okay? So basically, for similarities, I have a solid embedding. But for talking, I need another embedding because in an embedding for similarities, apple and orange are similar. In an embedding for talking, you want to know what the next word in a sentence is. So you want to optimize for similarity being the next word coming in a sentence. So actually, it helps a lot if I modify my embedding so that I go from the similarity embedding to a good talking embedding. And so basically, if I have a good embedding for finding similarities, I can make it better for finding the next word using the values matrix. So the keys and query matrices are there for building my similarity embedding, and the value matrix is good for building the talking embedding. And the idea is that the value matrix, I use it here to multiply the existing similarity embedding and get me a new one. That sounds like a bit of faith is involved, but that's kind of what happens in the neural network, right? So a little summary of attention. I think I got about 10 minutes, right? So a little summary of attention is I got my self-attention here. Check it out. I have my KQT transpose, which is the dot product, my divided by square root K. Those are the ones that give me my embeddings, right? And then I have this part, which makes it move. Makes it move to the left, to the right, up and down is the gravity part. But then the math multiplication, what it does is it turns this into an embedding that is good for talking. And then the distances are calculated here. The movement happens here. Here I calculate where to move, and here is where I move. And for multi-attention, for multi-head attention, same thing happens. My key and query matrices give me a lot of different embeddings. Some of them are good, some of them are bad. My values matrix turns these into good talking embeddings. And then this concatenation part basically concatenates these three embeddings. How do I concatenate them? Well, imagine if you have something two-dimensional. It's like a table of two columns, right? So I have three tables of two columns. I literally just concatenate them into a table of 6 columns, and now I have something in 6-dimensional space. So I have something huge. This is too big. because I have many of these embeddings, right? In the original paper, they have 12, but you could have way more. So this is a space that's too big. That's why the linear step brings it down to 2. So it says, I want some of them are good, some of them are bad, some of them are so-so. I'm going to combine them and bring this all the way down to my original, kind of an average, but a weighted average, right? And that's it, right? Now the question is, how do you find the key and query and value things? Well, the answer is you find them using basically training a neural network. This key, the K, the Q, and the V get trained as weights in the neural network. So if they're better, or they enhance. If they're not good, they get smaller, just like a neural network. So there's some faith involved here, but that's the idea. So here's the multi-head attention. All right, I think I have about 8 minutes, and we're missing a few things. Feel free to throw in questions in the chat, but I think the next are going to be pretty quick because we went through the hard part, which is attention. Let me do the softmax. So softmax is basically to turn things into probabilistic, right? So I have in the store, let's say I have the sentence, in the store I bought an apple, or the next word can be apple, orange, or elephant. So the transformer comes in and scores these, right? So let's say it gives us high scores to apple and orange and a low score to elephant. And I want to turn this into probabilities because I don't want the transformer to always answer the exact same thing, right? I want it to answer something that's different every time, but that's likely to be correct. So I want to turn this into probabilities. And one way to do it is to divide by the 3 of them, by the sum of the 3, because I need them to add to 1. But just like before, we don't want to have potential negative numbers, right? Like I could get these 3 numbers and sample out of here, but I don't want that, right? Because if I have something that is negative, I could get a 0 in the denominator. So let's do the usual trick, which is to take e to the score, right? I don't want to have negative probabilities. So I want to take e to the score. So if my scores are 4, 3, 1, minus 1, I take e to the score, e to the 4, e to the 3, to the minus 1, and then I divide by the sum in order to get probabilities. And now I get a high probability for apple, a high for orange, and a low one for elephant, because I'm not going to answer the word elephant in here. So basically, in my neural network, if my neural network gives me a bunch of scores, I look at those scores, I take e to the score, I then divide by the entire sum, and I get a bunch of probabilities, and this is a pretty solid response, because if I sample from here, I'm going to sample a word with a high probability. I'm not always going to answer the exact same thing. So that's what the softmax does. Then let's do the tokenization one. I'm not going to talk a lot about tokenization, but basically the idea is that these transformers have a bunch of tokens, 1 per word, or maybe 2 per word. For example, write a story becomes 1 token for write, 1 token for 1 token for story, and 1 token for period. But the word doesn't becomes a token for word, and a token for doesn't, and a token for int. So it kind of breaks it down into existing pieces that makes life easier. There's a lot of work into tokenization. In particular, Jay Alamar has a really good blog post on tokenization. I will drop it in the comments in a bit. And the last thing I'm going to talk is positional encoding. So what is positional encoding? Well, here's a problem. Here's a problem that you may have in a transformer, right? If I have the sentence, no, it is good, and if I sentence, it is no good, well, it's the same words. So for the model, it's the exact same thing, right? It says, well, I'm going to put them all in an embedding, and I have the exact same thing. So the question is, how do you modify this in a way that it gives it order? And I'm sorry for the answer. It's not going to be as pleasant because it's not something super like talking about the context or anything. You literally pick some directions and move the words around. So I'm going to say the first word, I'm going to move it to the right, the second word up, the third word to the left, and the fourth word down. And I'm going to do that to both sentences. And now I modify them, right? Because the first sentence, the first word here is no, moves to the right, whereas here is it, moves to the right. So when I move them, now I get different stuff, right? So now I've been able to tell these apart. But why would the model know what I did? Well, because all I have to do is come up with a really good sequence of arrows. And if the computer starts learning these arrows, then it can decode it and be able to tell the order of a sentence. Okay, so we're trusting the computer to be able to unlearn this sequence of directions, and then I modify the first word by some direction, the second word by some direction, etc., etc., etc. How much to add to each word? Well, as long as you have something cyclical like this. For example, first word is this, second word is this, third word is this, etc., etc. These are the vectors that I move around. As long as I have something cyclical that makes sense, the model will figure it out. This is the actual formula: sine of position over 10,000. Why they pick 10,000, I have no idea. Divided by times 2i over d, where d is the number of dimensions and I is the position. And then what we do is, this is for even and this is for odd. Let me give you an idea of what this does. Basically, I have a sinusoidal curve, and what I did before in the circle was exactly what I'm doing here in the sinusoidal curve. I take the first word, I take the second word, I take the third word, and so on. And wherever it hits, these are the amounts that I'm modifying the words in the embedding, right? So I give two numbers. That two numbers gives me the direction in which I'm moving the word. And if I want more dimensions, because my dimensions, my embedding has two dimensions, but I would have one with, let's say, 1024, then I keep enlarging this sinusoidal curve, and that's why I divide by this number here. So I keep enlarging it and enlarging it and enlarging it, and then I play the same game. So how do I modify the first word? By I add the vector of all these numbers. For the second word, I add the vector of all these numbers, etc., etc. And then if you're training a big neural network, it kind of learns to learn this function somehow, and then it's able to undo it. So I got, sorry, Theo, I think I'll finish in a minute or two. I'm just going to summarize this, and then I see some interesting questions. So I'm going to summarize what we did, right? This is the architecture of a transformer. So when we have, let's say, write a story, well, first we tokenize it, right? We tokenize it into turning into a token for write, a token for a token for story, and a token for period. Then we do the embedding. Okay. Then we move everything based on positional encoding in some directions. So this becomes this. Then we feed it into the neural network. The neural network is a plain vanilla neural network will not really know how to come up with the next word. But when we add to these feed-forward layers a bunch of attention layers that pull everything gravitationally every time, then we end up with a bunch of good scores. And we take the scores, turn them into softmax. That gives us a bunch of probabilities. And then we sample out of these probabilities, and we would sample a word that's pretty good, and then we get ones. And I think I'm in exactly the hour, so I'm gonna go ahead and finish here by saying obrigado. Thank you so much for your attention. I am here for questions, and obviously let me do some shameless advertising. Check out the YouTube channel, Serrano.Academy. In particular, this talk was the summary of 3 videos: attention mechanisms, attentions with math, and transformer models. I also have a book if you want to check it out, Grokking Machine Learning. So muito obrigado. And I will, if Theo wants to add anything, or if not, I can actually go ahead and answer some of the questions.
Yeah, go ahead. I would just like to, first of all, thank you so much for the clear and brilliant explanation. It was very, very clear. Thank you so much.
Thank you. Thanks for, it's an honor to be here. And the crowd was amazing because they answered all my questions really well. So it really helped.
Thank you, Chef.
Thank you so
for
much.
the interaction.
All right,
Okay,
I appreciate it. All right, well, I'm gonna go ahead, and if you have any ones that I missed, feel free to ask me. The Fernando says, "Oh, this is good. Are there interesting approaches involving manifold learning and local transformations on this manifold?" I love that. I don't.
Very interesting.
I think, I mean, the key query and value matrices, imagine them as like more parameters in your neural network. So they get learned like the neural network. But I don't know. Yeah, I don't know. It'd be interesting to see if there's any interesting manifold learning. My assumption is that if you're training them at the same time, because the neural network kind of bends space to be able to put, you know, all your answers in some, all your yeses here and all your nos here, right? So it kind of modifies the manifold. And if you're at the same time as modifying the manifold, transforming linearly it may be something, there may be a lot more going on inside that we just kind of say, hey, big neural network work. So yeah, let's probably answer yes. All right, Antonio says, how to increase attention to one word in a sentence? Great question, Antonio. Yeah, so here's the thing. If I have a bunch of words in a sentence, all of them create attention, right? But the moment I'm adding a new word, I calculate the similarity with all of them, and if it's similar, then there's a lot of attention, and if it's not, there's not attention. So, for example, if let's say I'm ChatGPT and I've been talking for an hour, you know, and I come back to a topic that I talked about an hour ago, then the attention of what I talked about an hour ago is much higher to what I talked about 10 minutes ago, because 10 minutes ago I was not talking about that. Because the attention between what I'm talking, the similarity between what I'm saying right now and what I said an hour ago is much higher than the similarity between what I say now and 10 minutes ago. So that's how these models can actually understand so much, because what they do is they don't necessarily look so much at everything that's been said, but they look at at what I've said that is similar, look at that more. So it pays more attention to the stuff that's more similar. And that's why they can process so much, right? Because if I just try to remember so much stuff, I get confused. But if I have a way to say, oh, this is related to what I said at this exact time, then it's much better, right? So I hope that answered, but feel free to follow up. Fernando, again, this is a great question. This is in the positional encoding with design stuff. It sounds like you're including embedding into a Fourier-like approach. That is true. I never thought about a Fourier-like. It does seem like, right? Like it seems like I'm turning things into sinusoidal curves, right? Like it feels like I'm doing a transformation. It's really what I'm adding, right? Like the stuff I'm adding, it seems to be something like a Fourier transformation of something, because it turns a vector into its sinusoidal components. That factor that I'm adding, you know, the first curve is the normal one. The second one is very wide. The third one is even wider. So there may be some something arbitrary there going on. But there could be something pretty Fourier-like there, you know. I feel like these things, this AI things work well, and then later you start realizing what math you did. So I think you're in the right track of like you're starting to sort of understand the math that is happening in those things. So definitely keep taking a look at those at those observations, Fernando. Okay, thank you, obrigado, everybody. Thank you so much. Nice comments. Bruno says, the mixture of experts is a bunch of small LLM activated one at a time. Oh, that's a good question. In the mix, I don't know so much about mixture of experts. Like in this particular, it's embeddings, right? Like each embedding is similar. But I don't know in an actual mixture of experts if each one is an LLM. Do you know, Theo? Yeah, it's a.
I'm not
Where's
an
Joao? Is
expert.
Joao here? He would know.
No, unfortunately.
Oh, so sorry, Bruno. I'm not exactly sure. It's a good question, but I don't know. Let's see. Thank you. Fernando says the problem is that your transformations are global. Yes, they are. They are global. They modify the entire embedding. I don't know if there's any approach that takes little pieces of the embedding and works with them. It could be. It could be that you could take your embedding and only look at some and only look. There's Joao. He answered the question. There you go. Thank you. So yes, Fernando, the transformations are global, and I don't know if there's approaches where that would take smaller pieces, less dimensions, and play with them. A lot of times you do this in machine learning, right? You take random entries and use those instead. So it could be that you could play with that if your transformations are too big. But as for right now, everything in attention is global. Letty says, could you go more in depth into how multi-head attention can extract multiple relationships in texts? That's a good question. Let's see. I mean, the way I look at it, multi-head is one thing, but let's look at one head, right? One head is precisely saying, if I had an infinite brain, I could pay attention to everything I've said. But since I have a limited one, I'm gonna emphasize more on the things that are similar to what I'm saying now. So pay more attention to those and less to these. And then multi-head is simply just kind of a way to say, I'm gonna think with a lot of different heads at the same time. And so maybe one embedding is really good at a particular topic, right? Like if I'm talking about cars, and I have 12 embeddings, but like, one or two, seven of them are have no idea what to do with cars, but like one or two of them are really good at that. So it's like those two people talk more. I let them more vote, whereas the others not so much. But then I'm talking about food, and then this embedding that was bad at cars is now amazing at food. So now this one gets a lot more attention. Well, not attention. This one gets a lot more vote, and is able to play that attention game more. So that's kind of how I see it. Um, yeah, but I hope it answered. But feel free to follow up. I think Joao just answered a question. It says, I see it more as if you applied something like multi-head attention to the linear layers. I forget what question was being. Oh, okay. So was Joao answering
It
Bruno's
was about
question?
this Bruno's question,
Perfect. So
maybe.
yeah, you're applying multi-head attention to the linear layers. Exactly. Yes, exactly. Like each the neural network has a bunch of layers. We throw attention in each one of them. So this gravity thing happens every time. So like you basically your neural network modifies the space successively. It's just that each one time you apply attention. Next time you apply attention. Yeah, you do gravity, train, gravity, like so. I guess it that's what it does. But then he says, but then only activated them sparsely instead of combining them. And I'm guessing that the reason is because of similarity, right? Like if you have it, it combines them, but in a way that is stronger based on which one is doing better. So let me know if that's what you meant, Joel. um, Eduardo says, can process sound with multi-dimensional and video with Fourier transformation at the same time? Ooh, that's a good question. Can you process sound with multi-dimension and video with Fourier transformation at the same time? Multi-dimension. I'm not sure if I understand. Oh, can you process sound with multi-dimension and video? I don't know. That's a very good. I don't know. Maybe you can. Yeah, like you could do. Are you saying it rather like an attention mechanism with sound and video at the same time? So maybe you can elaborate on that question a bit. So as I didn't fully understand it. Yeah, but my guess is you probably can. Yeah. Pranay says, are transformer good compressors? As in like PCA, kind of like compressing information. Like, are they good at summarizing information? Well, I mean, neural networks in general. Let's see. As in, like, can I do dimensionality reduction with a transformer? Right? Is that what you're saying? Um.
If you could explicitly
Okay.
say more about this question, I can.
Yeah.
Pranay,
You
please.
wanna say something?
No.
Okay. Sorry. Yeah. My guess is maybe they are, because a neural network understands data, and to understand data, you kind of have to compress it at some point. Like at some point, you have to have or expand it, but there may be somewhere in the transformer that you've sort of brought it down to a smaller latent space where things are understandable. So my answer is maybe yes, but it's somehow hidden. Um, oh, Fernando did his postdoc in the same department that I did my master's in an undergrad, and he knows my advisors, Ian Gould and Jackson. Okay, hey Fernando, shout out, shout out to Waterloo. Um, all right, Joao says I recommend checking something like what does BERT look at? Analysis of BERT's attention, and also like the mechanistic interpretability literature to see how different heads learn different patterns. Ah, that's interesting. Okay. Yeah, it's interesting how how different heads of attention. I mean, in a neural network, different neurons learn different stuff by by just that's how they work, right? Like to optimize something, you can't just make everybody good at the same thing in a team. You have to make someone good at one thing. It's like football, right? Like somebody's good at being a goalie and somebody's good at being a forward, right? A neural network does that. Like some neurons good at something and some neurons good at another thing, and that's how you solve the problem, not by making them all good at one thing. So attention to me, believing in multi-head attention has the same thing as believing in a neural network. If you believe that a neural network can successfully take different neurons in different directions and have something completely different functions, then same thing with a multi-head attention. Some embedding may be amazing, some of them would be amazing at other things, right? But definitely take a look at BERT attention as Joao suggests. If you have any paper you want to throw there, I mean, feel free. Um, and then Fernando says, join that you can make them more sparse, yet it seems that it needs a lot of dimensions in order to be radically different transformations to different niches. My guess is, yeah, definitely you need a lot more a lot of dimensions. So by sparse, I wonder, yeah, by let me see. Yeah. Oh, now this got into a really good conversation. How are you doing with time, by the way, Theo? Are you good?
Very good.
Okay,
Very good.
just feel free to stop me. I'm just reading. I'm learning.
That's perfect.
Um. So Fernando says you can make them more sparse. Yeah. Actually, what do you mean by making them more sparse? Do you mean like taking some dimensions, like if you have an embedding and you take some dimensions out of them, or by taking some heads of attention? Uh, Let me know. Eduardo followed up and he says, sound retrieve individually from archive and applicate one form to each. Unfortunately, I don't know so much about Fourier transformations. I know how they work, but I don't know how they're applied in sound and video. So it sounds like you're combining Fourier analysis with some kind of mixture of experts, right? Which is kind of what it does, right? Like a Fourier analysis kind of takes a wave and splits it into fundamental waves. So I'm wondering if there's any connection with what that's doing and what we're doing with embeddings, which kind of splits them into their maybe the components. Like maybe each head takes care of something in the same way that different waves in a Fourier transformation are able to each one be good at something. So yeah, definitely something to think about. Y'all says always mixture of experts are hard to explain just in the YouTube comments. Haha, yeah. Definitely. But the point is that as a single model, not multiple small ones, but you don't use each feed forward, each layer completely to reduce the inference cost. I see. So you're training a single model. Oh, like dropout, kind of like let's say you have a big neural network. It's not necessarily 10 different neural networks. It's a big neural network, except you take some chunk of it, and that's one expert. You take some chunk of it, and that's another expert, and then you kind of train them separately. Kind of like dropout, right? Which is you train a neural network by looking at some nodes and training them, and then training some others. So I hope I interpreted that correctly. Fernando says, regarding compression, as pointed out, combining with encoder decoders would be also a good approach. Yeah, that makes sense, right? Because an encoder, what is it, right? Like you have your big data, you have an image, and you put it through a neural network to try to get the same thing. And here you shrink it, right? So it's like a big space, and then it becomes something small, and then it's go back to big. And if you did it correctly, then this was a good compression of your image. So for example, a face, this would be like the eye, the color of the eyes and shape of the nose. It just brings it down to less embeddings. I feel like somewhere in the transformer, you have text here and text here, and somewhere in the transformer there may be some layer that understood this in a good latent space. Now I'm just guessing. I see a lot of the conversation is very good, and I think I'll let them continue the conversation there. And I'm gonna jump to Pranay's question, which says, "What do you think of OpenAI's new model O1?" I think it's creepy how good it is. Have you played with O1? It's amazing, and I think the special thing, obviously, more data, more computational power, just a better in overall. And I think the fact that it knew the weaknesses of the first one and now capitalize on those is good. But I think the main thing about it, and I don't know exactly the details, but it does some kind of chain level prompting. So it still finds the next word, which still bothers me, but hey, it works. But I think it does a bit of thinking. For example, let's say I'm going to tell a story with ChatGPT, a book with the entire, with a transformer model. I will, 1 second, please. I will, for example, I make it write a story of 10,000 words, guaranteed. The name of the protagonist in the first page is not the same one as in the last page, because that thing at some point is going to run out of window, right? So it may not be consistent. However, how would you create a good story based if using a transformer? Well, you could just kind of create a small summary of the story, and then there's consistent. The name of the protagonist is the same one. And then take each part of it and enhance it into a longer thing. And then each one of them and enhance it more. And then continue enhancing it, and then always tied to the previous layer. So it's like a tree of enhancing the story. And then you can get a consistent story where the protagonist's name is going to be the same and the story is going to be consistent. And I think O1 does a little bit of that. Like, I think O1 sometimes, when it's a complicated question, is able to break it down, answer each one separately. And so that is what I think, in the sense, theoretically, that's the impressive move, and the others are just technological moves. Yeah. So
Very good. We had like a very good discussion here.
yeah.
Thank you for all
Pretty good discussion.
contributions here. Very nice discussion. Unfortunately, we are running out of time. Unfortunately, but amazing presentation, amazing content. We are always learn something. Thank you so much, Luis.
Thank you.
Thanks.
Thank you, Theo. Thank you for the invitation. Thanks for having me here, and thank you for everybody in the audience for your attention. So it's just an honor to be here. Thank you.
Thanks for your attention. Yeah.
Thank you. Bye-bye.
Bye-bye. Okay, everyone, if you like to give us a feedback, please enter the link down below here in the comments. It's in Portuguese, I'm sorry for that, but give us a feedback. We would really appreciate that. Thank you so much. Okay, see you in the next talk in about 8 minutes. Okay, see you. Bye-bye. Please.